Okay, our next speaker is James Hebden, otherwise known as ec0, and he'll be talking about its UNIX system, Intel ME, JTAG, and open source BIOSes. So let's welcome James to the stage.
Thank you. I want to start right out of the gate by saying that I feel that Jurassic Park is the best hacker movie that's ever been made, and I know that's an unpopular opinion. But it is. So, my name's James, and my background's not that important, but I'm right into hardware security, hardware hacking. You can find me up at the Hardware Village for the next couple of days. I'm right into open source, like hardware liberation, all that kind of stuff. So what I'm going to be talking about today is very near and dear to my heart. I've spent a lot of my own time coming to understand all this sort of stuff, and the format of the talk is kind of less dropping mad 0 days and more of a public service announcement about all the weird shit that your computer does that you probably don't know about. Okay. So I wanted to start by sort of just giving a brief overview of actually what happens when you turn on a computer, a mobile phone, anything with a processor in it, basically. The CPU die has built-in logic that will essentially hold the processor in a certain state until all the voltages stabilize, at which point it resets. At that point, the CPU starts looking for code, and the place in which it looks is called the reset vector. It's a technical term for basically a fixed memory address that gets assigned when they design a processor. For Intel and AMD processors, it's just hard-coded in the chips. It's the same because they use the same architecture. For ARM, it's another address, but basically, once the voltages settle, your processor resets, start executing code. You can see the addresses here. These have been the same for decades and decades and decades and decades. Nothing has really changed in processors from this perspective for a super long time. There's actually some pretty cool tricks that go on in a processor to start loading code and start getting a computer ready to be a useful computer to humans. And that all starts after the processor jumps to the reset vector and starts loading code. An example here is the Intel series of processors. When you have a CPU is not smart enough and doesn't have enough logic in it to actually bring itself to life. You need supporting circuitry. Typically these are called north bridges, south bridges. These are just extra chips on the motherboard that basically give the processor what it needs to start up and start executing instructions. In sort of more recent Intel chipsets, we're talking about the North Bridge doing things like loading code from a flash chip and poking it into these addresses. So basically, CPU fires up, voltages settle, resets at the reset vector. The North Bridge has already come in and done some weird stuff to load the contents of the flash ROM on the system board into these addresses in L2 cache on the CPU. So it kind of tricks it into thinking like, hey, you've got this stuff in memory, you should start executing it. ARM does a similar thing. It's typically more implementation specific, and it's typically baked into the CPU design. Example being on the Raspberry Pi. Basically, you've got like a stage 0 bootloader that gets loaded from an SD card, and the logic to do that is actually baked into the CPU. And it will basically take that boot 0, again, poke it into the CPU cache, and away you go. You start running your very, very basic bootloader. All of this is absolutely invisible to the user, which is kind of the important thing here. It's normally binary, it's normally source code, you normally can't change it out. There's usually not free and open source implementations of this stuff at this level. But it is very important to actually bringing up the processor and bringing up the processor to a state where it can start addressing peripherals. And essentially, once you've been through this state, the processor is in a sort of situation where it's able to maybe start looking in SPI flashes or, in the case of ARM, on an SD card for the next stage bootloader, which I'll refer to generally as boot code, but we're talking about BIOSes, UEFI implementations, and in the case of ARM systems, it's usually a closed source system, just a general bootloader. So the other thing that happens, and this is becoming more and more prevalent and a little bit spooky, hence the slide, your computer's also going to start up, and it's going to start up a series of support processes. This is less common on ARM systems. Intel and AMD systems have their own implementations of this. Technically, they're basically going to fire up as soon as everything has power. So they're not actually involved in the process we just talked about. AMD has a processor in their CPUs that does this sort of weird handshake with the hardware. We'll talk about that, but essentially your computer is going to also, in tandem to the main CPU, be spinning up a whole bunch of other processors, whether they're on Bluetooth chipsets, network cards, external bare metal control cards, and also the security processor in modern processors is going to spin up at the same time. So you've got all of this stuff going on. None of it is visible to you. You have no control over the code that runs on it. It's a bit scary. Once all of that's happened and your sort of stage 0 bootloader has gotten the system in a stage where it might actually start thinking about loading an operating system, that's when you actually load a bootloader. And that's always something like grub with Linux, GNU Linux, NT loader, which is Windows NT bootloader, LaunchD on OS X, iBoot on iOS, HBoot is the really common bootloader on Android systems, and UBoot on most routers. These are a little more common, a little less implementation specific, and there's a tendency for these to be open source. So for example, UBoot is open source. iBoot is, despite Apple's intentions, now open source, not licensed. Grub is obviously the grand unified bootloader. It is a GNU project, and it's totally open source. So this is where you probably, as a user, have the first opportunity to start controlling what's actually happening on your computer. Obviously, if you run OS X, you've said, I don't care. And if you run Windows, you've said, I don't care. I trust you, Apple. I trust you, Microsoft. Interestingly enough, obviously, these things being open source doesn't make them secure, because often the version of U-boot that you're running, the version of Grub you're running, it's not necessarily up to date. Like that's on you to keep that up to date, basically. These pieces of software, their sole role in life, their whole reason for existing is to take your computer and start looking at storage devices where they might be able to load a more complicated operating system. The examples are here, of course, OS X, Linux, iOS, Android. These are all way too big and complicated to actually fit in the CPU die or fit in like a small boot flash. So you have these stages of the boot and a lot of code running that you never see. So we talked a little bit about coprocessors before, and some more examples of things that might be happening when your machine starts up. Things like firmware. We've got Bluetooth chipsets in laptops and phones these days because it's super convenient. Those typically have a small service processor in them that run binary-only firmware to actually do the Bluetooth bits. Those have essentially got potential attack surface on them because, they're RF devices, they can be interacted with from outside of the machine. These are almost always required to run the chip, and they're almost always closed source. You're essentially, by having Bluetooth enabled, trusting the vendor of that device that they're being proactive about security and that they're bringing you new firmware whenever they find an issue, and that they even think that issues are a real thing. You've got things like add-on cards, PCI boot ROMs, for example. When you boot a computer over the network to deploy it, say, you're going to be running like a PCI add-on ROM, it's called, and it's essentially something that gets loaded into the BIOS. gets executed from a flash chip on the PCI card, network card, and it extends the functionality of the BIOS. There's not a lot of security or signing around these usually. You can load alternate free open source boot ROMs on a lot of cards. A lot of Intel cards have the ability to load things like IPXE and GPXE to replace the vendor maintained chip contents. And people don't do that stuff though, really. So you're typically running potentially the firmware for these devices that the system came with. Firmware, boot ROMs, BIOSes typically don't get updated too often because you typically also have to reboot the machine, right? And that's very disruptive. When you take that out to like the enterprise scale, you take that out to production servers, the stuff's just not happening. It's just not on people's radar. Sort of like a third real class of systems here and coprocessors that are starting up are lights out and BMC management cards. Examples of these are like the Dell iDRAC or HP ILO, IBM RSA, I think they still call it. I think it's got a flash new name, but they're basically all ARM processors sitting on a PCI daughter board with a full OS, like full embedded OS running on them and network access. And they've typically got access, if not to the host OS via drivers that are installed in the host OS, also via, like you can just reboot servers with them. It's typically weak authentication on them. Most people use the default passwords. And typically you can get into like a shell mode on them. So again, you'd sort of know you had one of these cards. This wouldn't sneak up on you, but they're not something that necessarily gets updated very often and can also present a bit more attack surface on a system. There's been stacks of CVEs for these cards. If you go to any CVE database, just search Dell iDRAC. It's eye-watering. Authentication bypasses, code execution, and people don't update them. So they're often a really good place to start if you're trying to cause some havoc on an enterprise network. I really just wanted to use this GIF. That's why this slide exists. But yeah, look, I mean, in summary, boot code is there to bring the system up. On system on chips, it's typically referred to as like a stage 0. All of these things essentially perform the same function, which is to make a computer usable. The main sort of key thing with the boot code, which is, you know, BIOS, UEFI, it's almost always closed source. We find that with the firmwares, we find that with the stage 0 bootloaders. Boot code is typically only generated by a few companies in the world. American Megatrends are an example. Inside BIOS, Intel's got a reference UEFI implementation they call Tiano now. And they've got this really great catch-all around licensing, which means that they don't have to release the source code. The trend away from open sourcing the code for these is often speculated to be related to government backdoors is a really common theory. Licensing is usually the defense, but due to the system-wide access that UEFI firmwares and BIOS have, it's pretty common for people to want to, especially in the hardware liberation kind of community, want to replace the boot code with something a little bit more palatable, a little bit more open source, and something they can sort of inspect and sort of know is secure, and also just add additional features to old hardware. Boot code is something that often limits the usability of older hardware. In recent years, we've sort of seen technology head towards a direction of locking users out of choice. Kind of similar to what has happened over the years with gaming consoles as an example. We're now in a situation where essentially if you buy a gaming console, you are essentially buying a license to use that machinery, but if you modify it, you're breaching your EULA. Technologies like UEFI Secure Boot, they sort of come with these cool words like secure in the name, and they can improve the security of a process. There's a real potential for someone to load, I don't know, like a malicious kernel modification that then, you know, could be a real way into a system. If you have kernel level access to a system, you're essentially root or administrator. There's nothing stopping you doing what you need to do. So locking down using encryption and like key signing, the actual kernel modules themselves and the actual kernel is like a really good way to stop that from happening and to keep a system secure. The only problem with UEFI Secure Boot is most people turn it off, and you have to actually have your binaries signed by Microsoft. They're, by implementation, the only people who are allowed to sign things. You can install your own key roots, like a lot of system firmwares have that capability, but most people aren't going to go down that path. Like, if you want to say, like, hey, you want to run Mac, you want to run Linux, you've got to go install your own key root to have this secure boot feature enabled. People, they're not going to do it. So it relies on Microsoft actually ordaining an operating system to run on a system. It's kind of a flawed implementation for that reason. In even more recent processors, like Skylake onwards, I think it is, OEM systems have the capability of essentially burning into the CPU die a series of keys. Those keys are then used to authenticate the boot code, so the actual system BIOS, UEFI. Intel have an implementation of this called BootGuard. It basically relies on the processor and the system board being manufactured by the same person. And when they install the CPU into the board, they set a bunch of CPU fuses that contain the CPUs, and once they've been set, you can't unset them or anything, like they're burned in. This obviously stops people from putting alternate BIOSes on these systems. It also potentially mitigates the risk of things like bad BIOS, like malicious BIOS modifications designed to maintain persistence on a system. There's not a lot of evidence that this sort of stuff actually goes on. It's more of a theoretical attack, but you know, it's possible. So Intel BootGuard, designed to sort of keep the BIOS locked to what the vendor wants you to run. What's a bit awful about that is it sort of prevents you from modifying your BIOS, and we've started to see things like digital rights management technology built into system firmwares and essentially into the Intel management engine. There is a built-in system there for enforcing digital rights management, again limiting user choice. So it's another one of those technologies that sort of looks like it improves system security, and it does by all accounts. But it relies on Intel ordaining things and the vendor ordaining things, and the problem then is, you know, if you're not running like an open source BIOS or something like that, you have absolutely no say in what gets fixed or the functionality that gets added to your system. BIOSes suffer from bit rot. I challenge you to find a BIOS that got a meltdown or Spectre fix that was more than like 4 years old, and you actually might, but that's kind of here nor there. It's basically putting control from a security perspective of system firmware back in the hands of the manufacturers rather than back in the hands of the users and the security community in general. It's designed to minimize the attack surface, but yeah, it limits user choice. On the topic of sort of out-of-band management cards, like bare metal controllers, which we talked about earlier. So these are kind of interesting because they're essentially deliberate backdoors. You don't want someone to log into your system and have access to your screen, keyboard and mouse and be able to turn your computer on and off, but a lot of enterprise systems come with these cards installed. A lot of people don't change the default passwords on them. It's super common to find these systems on corporate networks with for Dell, root as the username and Calvin, whoever Calvin is, as the password. But it's kind of like an easy way into a system, really. And there's also like attack surface there because you can just wait out an administrator needing to log into the console. And people are not super diligent about logging out of the actual video card on servers. Once they've done what they needed to do, bring the server back up from like a power malfunction or whatever, they typically just close the remote management console, either leaving a root console or an administrator logged in console on the system. So if you can find one of those through the out-of-band management console, you're basically in. I mentioned before that these systems are kind of very closed source. They're actually like entire computers running on a chip. So security updates on these are super important. Like, I can't stress that enough, and people don't do them enough. So if you actually work in an enterprise that has lights out management cards, please update them. They're a very, very easy way for people to get into your systems. That's if your vendor is still actually issuing updates for them. In line with this, like, this is a feature that used to just be relegated to enterprise land and like really expensive servers, like several $1,000 chassis systems sit in data centers. As recently as like, it's less than 10 years ago, so it's recent in CPU land, Intel introduced a functionality called Amd vPro, you might have seen labeled on your new Dell workstation. And this is essentially, in its earliest incarnation, an ARC processor sitting inside the CPU die, running its own operating system with access to the network card of your system, designed to provide lights out management on workstation class systems. I mean, like, those words should be pretty scary, but they scare me. And it's another one of those situations where a lot of people buy hardware with these functionality enabled. They don't configure it, they don't change the passwords, and again, back to the point about vendors potentially not really giving a shit about updating these things and taking security seriously. There's been, a couple of like really notable CVEs against Amd and vPro that have allowed unauthenticated access to the Amd web interface because it runs a web server. Of course it does. And actually the attack vector was just not supplying a HT digest when you authenticate it, and that just lets you in as administrator. So pretty cool stuff, pretty like security 101 kind of stuff. And one of my favorite things is like this idea that someone designed this feature and would have been super excited about it and would have been like, oh wow, we can do this amazing stuff in the CPU, we can control it from anywhere in the world, we can turn the machine on and off, we can give access to the console. Never at any point in the process did they go, oh, actually that's a really bad idea, that's a really huge security issue, why do I want that? But sure enough, Intel baked it into the processors. In doing so, a lot of hardware liberation community and like hardware security community raised an eyebrow. Like, hey, this maybe isn't the best idea. Have you guys thought about the security implications of someone breaching this processor? Typical vendor response. We've had the CVEs there to show that it is important to consider this as potential attack surface on systems. One of the main reasons that this was implemented anyway, despite the security implications, is when you're managing thousands and thousands of workstations in an enterprise network, and you get a call from, you've got your help desk centralized somewhere cost effective, and your cost effective help center is having trouble walking the user who's calling through the process of rebooting their machine, because that fixes all problems. Being able to actually just log into the vPro interface and kick off a reboot is super helpful. Saves a lot of time, saves a lot of unnecessary hardware replacement. So, this is enterprise driven. It's not as common in home systems, but all of the bits and pieces are there, right? Like the CPU supports it, most of the system boards support it, but it is focused on fleet management in enterprise environments. And even though it's an enterprise environment, I've worked in enough places that don't actually configure it to be secure that I have opinions about it being there at all. So talking about processors that are embedded inside processors, AMD's got their own thing, which is called the Platform Service Processor. Platform Security Processor, it's right there on the slide, James. It's present in 16H and higher AMD processors. So like the much older, like Turons and things like that, they didn't have this. Essentially, hardware initialization on AMD processors is currently and was previously handled by an open source library called AGESA, AGESA. And that was totally open source. So the sources of that had been provided to like a bunch of open source firmware vendors and projects. And basically it meant that you could write a firmware for an AMD processor and all of the hardware bring up was handled for you by this library. When they introduced the security processor, they moved all of that responsibility into this, it's actually an ARM processor. So it's an ARM processor inside an x86 processor that provides all of the security features like TPM. And it also is heavily linked to hardware initialization. So you actually can't turn an AMD x86 processor on without the tiny little ARM processor inside saying it's okay and setting up all the memory timings and everything. So it's super embedded. Yeah, it's like an A5, so it's reasonably powerful. Like it's not like the ARC cores in the early Intel processors were really underpowered, like 100 megahertz or less. This is a Cortex A5. It runs a full real-time operating system inside. I mentioned it implements things like the TPM, so what that means is that inside the flash regions which are allocated to the platform security processor, you've got user credentials, you've got encryption keys that people have stored in the TPM, because the TPM on these processors is a software device, it's not a hardware device. You know, it'd be really sad if there was a CVE that allowed code execution on these processors. They also have access to the host memory, which is pretty cool. So if you theoretically got into one of these machines and had code execution, you would essentially have read-write memory access to the host. I have a diagram here. It's kind of small, unfortunately. It's meant to show you all of the stuff going on inside that little ARM processor and how it's just part of the ARM, like the AMD processor. We talked about the TPM. There have been vulnerabilities, so you can absolutely achieve code execution inside the TPM on these processors. There's also been a lot of the recent security announcements, like Amd Flaws. The former was a very legitimate security issue. Like it basically meant you could dump credentials if you had access to the TPM. Amd Flaws is a little less, it's more of a persistence thing at best. It was really played up as like, you know, the next big security issue, but it really looks like it was probably just stock manipulation. You need like local admin on the machine to exploit this, so at best you're using it to like inject code into the platform security processor to stay resident, but it's not actually giving you any sort of extra privilege that having local admin on the machine wouldn't give you. So ARM processors also implement a similar thing. Just whilst we're talking about AMDs, I mentioned it was an ARM processor. ARM Trust Zone is a security implementation for ARM. ARM is the security implementation for AMD. AMD runs an ARM processor for security, and that ARM processor also has its own secret processors inside it under Trust Zone. So, you know, yo dog, I heard you like coprocessors. Basically, ARM Trust Zone is actually not so much individual CPU dies. It allows you to partition an ARM processor into multiple worlds, they're called. So they're just like memory regions, certain memory allocated to what's called the secure world, or SWD. It's totally invisible, and it's also inaccessible to the normal world, which is where your code runs, your little blinky light demo that's running on your Raspberry Pi. Actually can't see the secure world at all. And on ARM processors, things like, you typically only see these in really expensive ARM systems like server systems, but they have TPMs and all that sort of stuff built into them to make them competitive as server systems. But they're actually, again, just software running inside the secure world on these processors. It's a little bit of a diagram. So orange being the normal world, blue being the secure world. The important thing to remember about ARM processors is they're actually extremely variable between vendors. So ARM only really sort of gives out generic reference implementations for ARM processors, and then it's up to the individual vendors to do something with that and do it securely, which always goes great. The secure world has this thing called the monitor running, which is actually what gates access in and out of things running in secure world. So you've got a TPM running in secure world, you do need to expose that to the normal world somehow so that you can actually implement an API to access securely the secrets. And that's the monitor's job. So there's basically special registers that get set when you're running code that are authenticated by this code that is running in the secure world. They're kind of like interrupts that you can fire, and you can pass parameters. So what actually happens is the execution of those instructions then has access to the secure world really briefly in like a certain way that the secure world has to respond to. So it's essentially kind of like a REST API in a processor. It's pretty heavy duty stuff, but essentially it means that you can have specific calls running to access the secure world to retrieve data, and basically that's available to the normal world. And like most APIs, it has security vulnerabilities, which is exactly how the TPM code execution was achieved. There was, I think it was actually a simple buffer overflow in one of the APIs, and once you've got code exec in secure world, you've actually got access to the entire host memory. Whatever you're running in there can't be seen by normal world, so it's super nasty. I also mentioned the implementations are extremely vendor specific. So, for example, Qualcomm, their implementation of Trust Zone is called QSEE, and Qualcomm Secure Execution Environment off the top of my head. And they also had a CVE that was code exec in secure world, and it was an API that they had implemented in the secure world to allow access to like media files or something, and it basically allowed code exec because it's just an API and they didn't write it well. So the main thing I think that is probably the most interesting about this world of coprocessors and like secret code and all that sort of stuff is Intel Management Engine, and there's been a lot of focus on the Intel Management Engine. I think quite rightly. It's been around for a while, so sort of post Core 2 Duo were the very early implementations. It is the hardware side of AMT and vPro, so it's actually the hardware implementation that is basically allowing AMT, which is a sort of software product, to dial into your processor and to dial into your system and do things like reboot the machine or like mount virtual media, all this stuff that it can do. It's integrated into what's called the Platform Controller Hub, and that's essentially the majority of the functionality of the Northbridge chip on the system board, which has access to like all of your I/O controllers, all of your memory. It actually uses the host memory to run. Pre-Skylake, it looks something like this. So you have like your main CPU, any like operating system agents that are communicating with the management engine, AMT for example. You've got your operating system running on the main CPU. And then inside the Platform Control Hub, inside the Northbridge, you had a dedicated Arc core, which was running a real-time operating system. Anything in orange on this is essentially dedicated to the management engine. But what's problematic here is that the management engine is inside the PCH, so it actually has access to everything the PCH does, which means hardware sensors, the Ethernet MAC, which is super cool, and all of the I/O devices that basically hang off the South Bridge, which it also has access to. It also takes up a small amount of the slot 0 DDR RAM. There was actually a pretty cool YouTube talk with the guy who invented this. He's like super pumped about it, you know, this is a great feature. And he accidentally sort of mentioned that, yeah, it runs in the slot 0 RAM, so if you just like didn't have that in, the ME wouldn't run, and you could literally just take your first stick of RAM out and the ME would be neutralized. The actual operating system for the Intel Management Engine runs in a partition inside the BIOS flash. So for it to actually work, it requires the system BIOS to have a functional environment for it to load up and run as its operating system. If that doesn't happen, your machine will reboot within 30 minutes because it has it triggers a watchdog timer inside the CPU, so you can't really easily remove it. Inside that same flash, you've got the system BIOS, you've got the gigabit Ethernet firmware, etc. And so I mentioned it has access to the network card. It's able to basically coexist on the Ethernet physical interface on the system board and send and receive packets on the Ethernet network and respond to those, and that's how AMT is implemented. This essentially wasn't as scary because it was in the North Bridge, it wasn't sitting in the CPU die. If you disabled it, there were basically ways to disable it by setting flags in the SPI flash, and it was not that big a deal. Post Skylake though, they actually moved the Intel Management Engine into the CPU die. So it's actually sitting there. It's in Intel Atom systems, it was actually a Spark system, which I think is kind of cool. As like an old hardware nerd, that if you had one of these Atom systems, you also had a Spark. So relive the good old days. You in the newer systems though, it's actually an x86 core. So you've got x86 on x86. It's way harder to disable. So the tricks around just sort of setting the SPI flash flags that don't work anymore. We'll talk about the methods for disabling this, but essentially being integrated into the processor makes it much harder to neutralize. It's much more crucial to the running of the processor, and being in the CPU die, it has everything that the CPU can access. It can access. Recent research into the ME to try and sort of get an idea of like what it's capable of and what code it's running, because really if this is running inside the ME, it's running on your computer all the time and you can't observe it at all. Recent research shows that basically the processor has multiple unlock modes, and these unlock modes are controlled by specific encrypted flash partitions. If these partitions contain Intel keys, the processor will enter what's called red unlock mode, and there is essentially an Intel technology called DCI, which is a debug bus that they use when manufacturing and debugging Intel processors. And if the processor is in red unlock mode, you actually have a functional JTAG interface into the Intel ME processor. Basically what's required there is not for basically you need the Intel keys to get that mode, because red unlock mode needs the Intel keys. There were some recent CVEs against this though, which allowed code execution inside the Intel ME. One cool thing is like if you're familiar with like memory access, there's multiple rings in an Intel processor. Ring 0 traditionally being the highest, that's like the operational mode of the kernel and the BIOS and all that sort of stuff. Intel ME actually runs in ring -3, so it not only has access to everything, ring 0 can't see it, so it's totally visible. But basically there were CVEs that allowed code execution in ring -3 in the Intel ME core, which is an x86 core, that allowed Positive Security did a lot of really great research on it. There's been some awesome talks coming out of Black Hat and EU. And this code execution allowed dumping of the firmware. It allowed also for these guys to work out that there was a like secret undocumented unlock mode that didn't need the Intel keys and would get you into red unlock mode, which they did. And so JTAG was had, firmware was dumped, and yeah, basically they found out it runs UNIX, which is an educational UNIX operating system. This kind of corresponded with a bunch of emails back and forth from Andrew Tannenbaum, who's the guy who wrote UNIX, from Intel, where they were asking like loads of questions about UNIX, and he's like, this is weird, but okay. And yeah, they basically wrote their own extended version of UNIX for this. They haven't released any of the source code. Again, there's more speculation that that's due to government backdoors, but it's probably just because they don't want AMD to steal their shit. And basically, the ME is a Unix system running inside your processor, no matter like what host OS you run. You're running Minix, which is cool because Minix is kind of like the most commonly run operating system in the world now. So from all of this, like, there's a few takeaways. General coprocessor security, too long, didn't read. Security processes running closed source code beyond user control, which are hard to update without significant impact to the system. They don't necessarily improve the security posture in the long term of a system. The closed source processes, which control the initialization of hardware and which payloads they will pass execution to outside of user control, are bad for user freedom. So not being able to run what you need to run on your hardware that you've paid money for it's not only like a bit unfair, it's actually kind of preventing you from keeping that hardware for longer. It forces you to buy new hardware when maybe the hardware you've got is totally fine. There's like environmental implications for that. And also your computer probably has a backdoor in it that you don't know about. And there's not heaps you can do about that. From a hardware liberation perspective, there's options though. So you can basically replace the boot code on your system with something like Linux boot, Coreboot, or LibreBoot. You can disable security management processes like the Intel ME through various means. And there's also alternate firmwares being developed for bare metal management cards like OpenBNC. Linux boot is actually a kind of interesting project because it essentially means to replace the system BIOS with Linux. It's got essentially just enough to bring up the system to the point where Linux can bootstrap, and most drivers in Linux actually are capable of bringing up hardware without assistance from the BIOS. Mostly because BIOS are very unreliable for bringing up hardware unless you've got the secret documentation that they give to Microsoft. But yeah, Linux boot is essentially more of a server-orientated project. For end-user systems, and I run it on this laptop, Coreboot is becoming more of a common option. It's an open-source BIOS. Basically replaces your vendor BIOS and is enough to bring up your system, or like, unlike Linux boot, you can actually, press F12, boot off a USB. It's quite usable. UEFI is actually, there is a free and open source implementation of UEFI called Tiano Core, and that's actually part of the Intel UEFI implementation that they have open sourced. It's often used as a payload for Coreboot if you need to boot UEFI only operating systems. And then you've got projects like Heads, which is basically meant to coexist with Tails, and it's essentially like a verified boot option. So all stages of the boot process essentially verified with like public key cryptography. So as far as if you've got a coprocessor in your processor, what can you do about it? Intel ME, there's some kind of crap options. AMD PSP, you are so out of luck, it can't be disabled at all. Trust Zone, you can get lucky based on the vendor. BMCs, you can get lucky based on the vendor. By age, there are different means for disabling the Intel ME. The very early ones we talked about, the ones embedded in the platform controller hub, you can set some flags in the flash descriptor, and it will just not boot up. It's fine, it's gone. Nihilum and onward, you can run there's an open source project called ME Cleaner, and essentially what that does is it removes as many modules as it can from the ME firmware, leaving only the barest minimum modules that they've found are needed to send that watchdog pulse to the processor to keep it running. So the nasty stuff is more than likely in those other modules. There's absolutely nothing to say that the core modules don't also have nasty stuff in them. There is, as a result of the CVEs that have come out for Intel ME, the research that has been done by Positive Security, there's been another method found very recently using the JTAG interface, which is called Alt-ME Disable. And it is similar to the early methods of disabling ME where you can set a couple of flags in the SPI flash, and the ME sort of goes to sleep. Don't really, this isn't documented anywhere, but it seems to work. 2013 plus, Intel have actually implemented a high assurance platform support, which is not a public feature. It's been designed essentially at the NSA's behest, because funnily enough, they don't want secret processors running in their environment. And ME Cleaner now has support for setting that bit on the newer processors, and you can essentially disable the ME that way as well. You obviously can't do this on systems with Intel Boot Guard, because you'll be changing the contents of the system BIOS. It'll no longer verify, it won't boot. So OEM systems, systems that you've built yourself, for example, by buying a motherboard, buying a processor, there's no way the boot guard can be enabled on that combination. So you can absolutely disable the ME using that. And there's also vendors like Purism and System76 that are basically, they are hardware manufacturers and they choose not to enable this. When they set the CPU die, they set the fuses on the CPU, they don't, I believe they don't put keys in, so boot guard doesn't work. So you can still enable ME because you can modify your BIOS, and you can also run Coreboot on some of these systems as well. Talked about that, you can't run anything but PSP, that's your life. Trust zone, so certain vendors allow their processors to, you can't disable trust zone because it's kind of an inherent CPU feature that allows you to partition areas of memory, but some of the vendors will allow you to run code in it. So you kind of have access to that. You can sort of inspect it. You can see what's going on there. It's still not an awesome situation. For BMCs, you've got OpenBMC I mentioned earlier, or you can actually just often desolder the modules or pull out the BMC cards if you don't use them. But OpenBMC, funnily enough, is actually a Facebook initiative because they weren't happy with the stability of their bare metal controllers, but also they didn't like the idea of trusting a vendor to have access to their data, which is 10 out of 10 for self-awareness. And I figured I'd now just sort of go through a demo of a laptop I've disassembled, dumping the firmware, disabling the ME, flashing Coreboot, showing you what that looks like, which is going to involve me playing a video on the external screen. Of course not. Why would we work? Right. So this is a motherboard out of a Lenovo X220 that I've pulled. You can do a lot of this stuff inside the machine. Like, you don't necessarily need to pull the motherboard. A lot of systems just have the flash chip underneath the palm rest. You can see that's model hands that I hired, showing where the SPI flash is. One of the worst and stupidest things you can try and do is this, because it doesn't work. Basically, I have it in this video to demonstrate how futile it is. Unless you really dial up the temperature on a heat gun, it's very hard to remove an SPI flash for flashing. Because they're soldered onto the ground plane of the board, you've kind of got to warm up the entire board. So what you want to use is something like a test clip. And this is just a SOC8 test clip. You can clip it onto the board. You can see I've got the power supply connected to the board. That can be a really good way to supply enough power to the entire board and the flash chip. Often when you plug these things in, sweet, that's cool. That's what I wanted to happen. Oh no, that's intended. Basically, the power from your SPI flasher is not going to be enough to power up the whole motherboard, and because the chip's still soldered, that's essentially what it's going to be trying to do. That's probably not... Is that readable? Okay, cool. It's not readable for me. But so with the SOAK chip connected, there's a piece of software called FlashROM, which is just a really common open source piece of software that's used for interacting with SPI flashes. You can see this command I've run here is just a shell script that I'm using a BeagleBone Black to do the flashing because it's got a pretty decent 3.3 volt supply, which is important. It's also very fast because it does native SPI. So I'm just dumping out the firmware from that chip, and you can see it dumped just fine. So this is me powering up the laptop before I have made any changes. System vital data, not that interesting. You will be able to see though on the config tab when I switch to it. Okay, fine. I'll catch it this time. I prepared this whole video with a piece of software called OpenShot, and it was my... Anyway, you probably saw it flash up there. The Intel AMT is showing as enabled in there. I got some pretty decent effects, transitions and stuff, so I was pretty impressed with myself, but I didn't manage to pause it long enough on the AMT bit. So yeah, essentially you can see that it's enabled. It's the vendor BIOS, like you've probably all seen a ThinkPad boot up. What we'll do now is we'll go through the process of running Intel ME Cleaner on the flash that I dumped earlier. So basically taking the vendor BIOS, running ME Cleaner over it, which I run it with the -S flag, which also sets the high assurance platform bit in the flash. And then, yeah, we basically write the flash back to the chip, which is always way faster than reading the whole thing, because basically if there are any zeros in your flash file, it'll just skip over them rather than rewriting them. I promise I sped this up. So this is just doing a walk of the original flash, showing just the amount of stuff. These are all flash partitions. These are all mostly containing code and modules that are running inside the management engine. Just to give you an idea of the scope of it. So ME Cleaner will reduce this down to about 2 or 3 modules, depending on the edition. The rest of it is things like video drivers and things like that, because it interacts with the video card and all sorts of stuff that seems really unnecessary for a security processor. There's a lot. So yeah, this is basically ME Cleaner running over it. He's removed a bunch of stuff. So now we boot it up with the newly flashed, cleaned BIOS. So it firstly does boot after reflashing the modified BIOS, which is kind of cool. If we get into the system menu on the BIOS, you see the AMT option's gone, so it's essentially disabled it. This is essentially the compilation of Coreboot. Being a free and open source project, you sort of have to select your board. It supports a whole bunch of different hardware. I've selected the X220. It supports a number of payloads. So when you run Coreboot on your machine, you are not just running Coreboot. So you can basically configure Coreboot to load what's called cBIOS, which is an open source traditional BIOS. You can configure it to actually load grub directly in the SPI flash, so you can direct boot your kernel or your OS. You can even load a Linux kernel in as a payload, so you actually really cut down the amount of code running on your machine. I've gone with grub here. One downside from filming this demo was that I learned about halfway through, it actually made me super glad I wasn't doing this live, is that you actually can't get an external monitor working in Coreboot apparently. Compilation. So I'm just flashing it and then running ME cleaner over the Coreboot binary because Coreboot needs the ME firmware as well to keep the processor up and running. And it's firing up on the laptop screen now. And you can see it boots straight into grub. So no vendor BIOS anymore, ME disabled. And you can embed a config file so it boots your kernel and everything like that. For the purposes of the demo, I didn't, but that's essentially it. Any questions?
Thank you very much, James. Let's give James a round of applause. We might have time for one question before the start of the next talk, if there's any people out there that want to ask. Okay, great. We have one question over here.
So, how many systems have signed BIOSes so you can't run ME cleaner on them?
Sorry, I actually missed the last half of the question.
So, how many BIOSes are signed so you can't just run ME cleaner or modify them?
Pretty much any OEM system, so Lenovo, Dell, they all enable boot card, it's all signed. Pretty much the only way on newer systems is to go with a vendor who specifically doesn't sign their BIOSes, like System 77, Purism. They're not paying me any money to say that. Or build your own systems using sort of standalone parts. But they all enable it because it's a security feature. So.
Thank you very much. Just one more round of applause for James. And by the way, James mentioned this earlier, he is part of the Hardware Hacking Village staff, as is Paul, who is coming up next. So go see those guys tomorrow at the Hardware Hacking Village and they'll show you a thing or two.